Okay, so cloud computing is still growing in popularity, in scale and complexity, as we all know. And there's a similar increase noted in discrete and simulation tools for cloud computing. So since about 2009, there's been an increase in the usage of discrete and simulation to support modeling and simulation in the cloud. So these tools aim to analyze the behavior of data center resources, VMs running in data centers with very low user load or very low workloads. So some of the advantages of simulation for cloud computing, they're far less expensive economically than using a testbed typically. So a testbed can cost a lot of money, whereas you can simulate the same system, and it's far less costly to do that. Experiments can be run much quicker because you can run them in simulation time rather than real time. Experimentation is repeatable and potentially scalable, so you can repeat the experiments if you want to model stochastic inputs. You can repeat them over a number of replications and produce results that way. And also, they're potentially scalable up larger than a testbed. However, assumptions and simplifications might not represent a real system, so real testbed validation might be necessary. So you might want to validate against a real testbed or a real system before performing any experiment. So that's just a very high-level introduction. The background to this talk is that we've had two accepted papers in Closer 2017. So we've had two short papers. One is a position paper, one of the short papers, and the other one is a short paper. So the first one is a review of tools against specific high-level criteria. So we've defined the criteria to analyze the tools by, and then we've compared a number of tools against each other using this criteria. And the second paper is a preliminary systematic review of literature relating to simulation, open source simulation tools. So in that case, it was 256 papers surveyed between 2009 to 2016, focused just on papers in IEEE Explore, none outside of that. So looking at the first paper now, there was 33 cloud simulation tools identified, and these are the cloud simulation tools here, listed in alphabetical order. So you see 18 of them are derivatives or extensions of CloudSim. So CloudSim is the main tool in this area for both research and in practice. CloudSim is used, and there's tools built on top of it, or extensions built on top of it. And the rest of the tools then are either based on other software stacks, or they're built from the ground up. So the comparison criteria that we used was, we defined the criteria by the underlying software stack. So what software stack is underlying these tools, with licenses, the initial publication year, when they were first published. Also, the last time they've been updated as well in terms of the year. The lines of code, how many lines of code for each of the tools. Availability of user documentation, availability of source code, if the binary is available, the languages used to develop the tools, whether they're portable or not across platforms for Linux, Windows, whether they claim to have distributed architecture, the type of persistence used by the models, if there's an API available, if they have a graphical user interface, if you can run them headlessly without a graphical user interface, and what format the results are outputting. So looking across these then, so in the paper we've got the tables are presented like this, and I don't expect you to be able to read that. But just to pick up some of the underlying software stacks to start with, you can see that CloudSim is by far the most popular underlying software stack. Some of the other software stacks would include Omni++ or INET, or with INET, Gladio Simulator, and NX2 for Green Cloud. And some again are built from the ground up, which are CloudShell, CloudSim, DCU Sim, etc. There's two versions of DC Sim, so they're just called 1 and 2 here, completely separate from each other. So today in this session we're going to hear from iFog Sim is going to be presented, CloudSim will be presented, ICANN Cloud, and next up after me is Capital Sim. So we should get a kind of a spread of tools presented today in this session. Again, we've compared across the licenses as well. Just to give you some examples, CloudSim runs on Apache 2 license, iFogSim, same license. CactusSim has the Apache 2 license, GPL, and EPL as well. Lines of code for a number of simulators was also measured. This gives an indication of the development effort that's been put into the tools, and may give an indication of how complex or how useful those tools are. Saying that some of them again are built on CloudSim, which has a lot of code involved behind it as well. So some of the tools just speak about are CactusSim, CloudSim. At the top in terms of lines of code, down the bottom you've got CM Cloud Simulator with just 566 lines of code. In terms of publication year and last update year, so the publication year is the relative year that they were first published, and then the last update year was the last time that they've been updated in the repository. Just pick two examples. CloudSim was published in 2009. It was one of the first, if not the first, and it's still ongoing to 2016 with updates. Whereas you have the likes of UniSim, which was published in 2005 and hasn't been updated since. So you'd assume that just from that, you might make the assumption that that was just developed as a one-off simulator that was used just for one publication and may not be available. The source code may not be available, but you can check that against the other criteria here as well. In terms of documentation availability, surprisingly, over half of them didn't have documentation available. When I talk about documentation, what we mean in the paper is that documentation to support the users in terms of a user guide or a programming guide, rather than a published research paper, etc. So over half of them didn't have any documentation available, even if the source code was available. Source code availability, again, the majority of these were done as one-off simulation studies, or maybe one or two simulation studies published in papers, but the source code isn't available. MDC Sim is commercial tool in there, but it's commercial and educational, but we don't have the source code available. In terms of languages, by far the most common language across them is Java. Some of them are C++ based. 23 simulation tools based on Java. 17 of these are based on CloudSim, so you assume that they would use Java as well. 6 based on C++. In terms of platform portability, most of them claim that you can run them on either Windows or Linux. These three don't, UniSim, GDC Sim, and GreenCloud all run on Linux. There was 4, I think, that you couldn't get data on. In terms of graphical user interface availability, about a third of the tools have a GUI available for building the model or presenting and analysing the results. So that's the high-level feature comparison. But moving on to the systematic review. So there's 256 papers reviewed from 2009 to 2016.
Yeah, we could just ask you a question about when you showed earlier the lines of code, one of the CloudSim, or the original was it CloudSim, had 94,000 lines, and the smallest one at 500 lines of code.
Yeah, that was SimGrid.
So does this mean there's a huge range of features, and some of them are very little?
Yeah, I mean, some of them, like CloudSim, would have 28,000 lines of code. And because you've got so many simulators built with CloudSim as a core, some tools that are developed as separate tools may just have a small amount of code to develop additional features on top of CloudSim.
Oh, they sit on CloudSim.
They sit on CloudSim as the other line. But yeah, I mean, typically they're under 10,000 across most of them. CloudSim then will be up to about 28,000. SimGrid is what's for simulation and pre-computing, and it's evolved to allow for simulation for cloud as well. So it's a long time being under cloud, and it's still being kept up to date.
So there's an earlier
It's an earlier one.
Origin,
Yeah, yeah.
pre-cloud, or
Yeah, yeah.
I suppose even just to introduce Gabrielle into this, because ICANN Cloud is up there and it's a heavy code seminar. So Gabrielle, I suppose from your perspective, is there more features in ICANN Cloud? I know you're going to present ICANN Cloud anyway in the session.
It depends on the models that you include. So if you are modeling more components in detail, you need more classes and therefore you need more lines of code.
roughly how many things are being simulated? Many things are being simulated by these tools.
I will present later. I can tell you can see. So it's
So that one, yeah. Generally
depends.
speaking,
Yeah.
is there? Are we talking about 10 different variables or 100 variables, or what's being simulated?
For example, in the case of SimGrid, I think that is because it includes also the network simulator and all the capabilities. Correct me if I'm wrong, but I think that it includes all the capabilities of the network and everything. So another simulators, for example, another that are based in CloudSim, they use the capabilities of CloudSim for simulated networks. So they only provide the models of the components that they want to simulate, for example, GridSim or another one. So I think that that's one of the main reasons, because SimGrid has that huge amount of lines of code. And I can cloud it because of the models, for example. It provides a lot of detailed models in memory, disks, component virtualization, hypervisors. So
SimGrid also has, SimGrid is parallel distributed also, something that most of the simulators are not. SimGrid is also not just a simulator. It has a lot of features that go beyond the simulation of clouds and grids. It has the simulation of user access control, for example, or they also simulate cost, something it's not usual in cloud simulators. It's a very heavy and very big code, doing more than just simulating the cloud. Actually, it's a package. It's not a simulator itself. It's a whole package of things.
So is this a simulation of an application on the cloud, or is it something wider than that? Is it a simulation generally of the performance of this particular cloud service? Where's the starting point?
I suppose it can be whichever. I mean, it depends on the tool and it depends on what you're trying to look at as a goal of simulation. For Cactusin, for example, which is going to be something that's area, the infrastructure is modeled, the application is modeled in the workload concept. It generally focuses on one application, but with multiple applications we're also modeled using Cactusin during Cactusin. So I think it depends on the application.
If part of the application is on one's local server and part of it is on the cloud, does it take that into account? Does it simulate the whole lot? Or?
depending on the simulator, yeah, it could be, but depending on the simulator. So if it has the models to simulate only the cloud, you cannot simulate partially in HPC environment, for example, and externalize some part of the application to the cloud. But if the simulator support both environments, it's possible.
I think in systematic review, there has been something that the previous published which showed us types of similarities, and I have to go back to see if the tools were that's kind of specifics in there.
iFoxing does that. Yeah, iFoxing does that.
So this is one of the reasons why you're careful about selecting a tool.
Why simulate when you've got the cloud there and it's temporary and elastic already?
Why simulate?
Yeah, is it cheaper?
Yeah, I mean, if you want to, if you want to run applications, see your performance, if you want to optimize your system, it's difficult to do that on real system. So if you have optimization models in place that you want to run to try and optimize everything, it's better to try that out first. So to model the real system first in a simulated environment, try those things out, see what happens, and then you can validate that, run some experimentation, and do that in a real system. And you can do that with test beds, but test beds are costly to set up. and also it takes longer to run. I think the test bed and gap are results in it.
So is it all about performance then, or is it more than performance?
I think it's mostly about performance. Do you agree with that?
It's mostly so.
It's mostly about performance, I mean, improving performance in the system.
It's not necessarily about the integrity of the system as would be in a test environment.
I think that there are more things than the performance. You can analyze costs, and you can
Yeah.
analyze, for example, infrastructures or topologies that are not existing correctly. So you can go, for example, in simulation, you can simulate making some assumptions, but you can simulate a CPU processor with 1,000 cores, for example. That is not possible, but you can analyze the trends if your model is right. So you can go a bit farther, and you can predict what is going to happen in a few years, or you can study the behavior of applications, the behavior of the performance, networks, topologies, the impact on applications. I think that simulation is a very powerful tool from the perspective of trying to foresee not only to how much money is going to cost or how fast my application is going to run, is to have a secure environment where you can test the things before to deploy, avoiding to harm any user or any infrastructure. For example, to analyze any energy in the system, you need or invasive tools, or you need to monitor everything, and that's, or it's costly, or it's hard to do. It's quite hard. With a simulation, you can see the trends of the system under different conditions of the energy, for example. That gives you a clue of which things can you apply, or things like that. So that's the main
I'm actually just conscious of time because we have someone dialing in the one after this, and so what we might do is it would be interesting because some of the other simulators will be presented here through the session. So maybe if we return to this discussion, we can return to it on a couple of occasions, maybe through some of the questions. So maybe James, if you can just move on, and what we do is come back to that.
Yeah, so we have about 3 minutes left, but it might take a little bit
No,
longer.
work with it.
I'll just go through the rest of the slides here.
I'll give you 6, James.
Yeah, that's fine. I think we'll be finished doing that. I want to see how far I went. Yeah, so it's on this slide. So you can see in 2009, the first version of CloudSim was published academically. There was 2 papers published at the time, one of them was on CloudSim. And since then, there's been an increase in publications right up to 2015, where there's 78 publications identified in IEEE Explorer. 93% of these overall were conference papers, 7% journals. So we're expecting that there'll be a ramp up in journals in the future. The first journal was published in 2013, so that'll be 4 years after the first conference paper. 85% of the papers overall were based on CloudSim. So CloudSim is by far the most common tool out there in this space. So this is the total publications by year. Again, it's overall 256 papers. You can see here, CloudSim, 188 papers. Cloud Analyst is second with 18 papers. That's mainly because Cloud Analyst provides a graphical user interface for CloudSim. Green Cloud then is next to 12, and the rest are all quite low in terms of the number of publications. So in terms of papers, we can split them into 2 categories. 45 of the papers related to design, development, and extension of simulation platforms. And the rest of the papers are all related to using those simulation platforms to perform research. So again, CloudSim stands out as the number 1 with 10 publications related to the development of CloudSim. But the other 211 papers, we can classify these. So there's an attempt made then to classify them based on the taxonomy promoted by the DIMA, where in 2009, where they proposed a taxonomy of cloud based on the architecture, virtualization management, services, fault tolerance, security, and quality. And because so many fall under the area of virtualization management, there's further classification promoted by Singh and Shannon from 2016 related to resource provisioning, resource scheduling, and resource monitoring. So I'll just pick through these really quickly. In terms of architecture, so that includes private, public, hybrid, and federated cloud. The vast majority were public, can be classified as public cloud payers. Private cloud was 3 and 1, it's hybrid, and 10 were other payers. Services include IS, PaaS, and SaaS. 13 around the infrastructure as a service level was not specifically for platform as a service organization in that way, and software as a service, 3 to be classified as that. In terms of virtualization and resource management, for resource provisioning, 49 papers. Resource scheduling was 91 papers related to resource simulation for resource scheduling. And resource monitoring, 13. So by far most were simulation for scheduling of resources. And there's 14 for VM placement, 12 for VM migration, and 20 for other. Fault tolerance, there was 6 that were specifically simulating on cloud for fault tolerance. Security, 8. Because security is quite important, there was just 8 specifically in simulating security. Load balancing was 43. Interoperability, 13. Storage, 11. That's it really. So that's how the papers can be classified in the systematic review. So just to conclude then, clearly CloudSim is the main platform that's been used for research purposes, as I've said already. It may be advantageous to choose CloudSim based on the volume of research output, how active the simulation community is for support and updates, and how valuable the extensions are. But obviously, you choose a simulator that's most suited to your case or your goal in terms of the features that it supports. CloudSim is also an early simulator, and there may be issues with it that have been inherited right through. So some of the noted limitations of these studies is the comparison features they're at a high level. So there's a need for direct comparison features based on actual validated models, where you actually model or create a model and then try and model that across simulators and then compare based on that. And a systematic review is limited to the IEEE Explore library. So further servers are needed where you've got a wider set of publication outlets and maybe take into account proprietary simulation platforms rather than just open source. Okay.
Okay, thanks, James.